I've been obsessing over Popeye here. I find it interesting how this cartoon character can be a vehicle for so much discussion about micronutrients. And I've sort of been focusing exclusively on iron. We're going to finish up with iron and then veer off into some vitamins rather than the minerals here. But I was trying to get at the difference between vegetable and animal sources of iron because I showed you a chart last time that talked about the absorbability, another word for that is a bioavailability of iron from meat sources versus vegetable sources. And there's a couple reasons for this, and we're gonna explore them. One of them is the oxidation state of iron. Iron that's in vegetable sources is basically a free ion. It's typically not coordinated with, certainly not coordinated with a heme. And if it is coordinated or bound up with some other small organic molecule, it tends to be an organic molecule that's going to prevent it from being absorbed, not enhance its absorbability like the heme. But when it's free in solution, the Fe2 plus that we find in most vegetables is not readily absorbable. It's not very easily soluble. It's not as soluble in water, is what I'm trying to say, as Fe3 plus. Or pardon me, the opposite. This is true. Yeah, that's true. Yes, Fe2 plus. I'm sorry, I have a bit of a head cold right now, so my brain's moving slow. But ferrous iron, Fe2 plus, is not as soluble. Fe2 plus at physiological pH is more readily soluble than Fe3 plus, which tends to be more insoluble. And when it hits the stomach, Fe2 plus becomes Fe3 plus. We do absorb some Fe3 plus, but it is not as readily absorbable as the other reduced form, the Fe2 plus. Okay, does that make sense? So the form that the iron is in the spinach is more absorbable at that pH, but when you get it in the stomach acid, it oxidizes it and makes it less soluble, harder to absorb. All right, so this is one of the problems. Your stomach acid makes the iron harder to pick up out of vegetable sources. Cool? Yeah, got to clear the cobwebs out of the brain here. The other problem is there can be all kinds of things that coordinate with the iron. Some of them can enhance the absorbability, and one of those is vitamin C. We talked about citric acid way back in the beginning of the semester when I was talking about Carl Scheel, who was one of the first people to identify oxygen. He also identified citric acid, which is a form of vitamin C. Ascorbic acid and citric acid are two different interrelated molecules from which we derive vitamin C. So ascorbic acid can coordinate with iron and enhance its solubility. All right, and there's a lot of different ways that you can coordinate the iron and the ascorbic acid. You see along the bottom there those panels A, B, C, and D. I don't, of course, expect you to memorize any of those structures, but it's to show you that there's a wide variety of complexes that the iron can form with the ascorbic acid. So often in vitamins, like a one-a-day vitamin, you're going to have iron compounded with some vitamin C in there to try to enhance the solubility and the absorbability of the vitamin C. So ascorbic acid or citric acid, vitamin C, whatever you want to call it, all of those enhance, they coordinate and enhance the absorbability of iron. On the other side, there's another molecule called oxalic acid. Now, oxalic acid or its conjugate base, oxalate, are so oxalate, the conjugate base, coordinates iron really well, but unfortunately, it reduces the absorbability of the iron. So,
what does coordinate?
To coordinate something means to bind it along. So you have this iron center, and there are it is able to form a certain number of bonds around it, and those are the coordinates around that iron that whatever is binding to that metal ion. So any metal can coordinate something. The coordination, it just means the binding of an organic molecule to the iron center. Yeah, Damon. Heme is the organic framework that surrounds iron in a hemoglobin. So the globin is a big globular protein, and there's this like trampoline meshwork that's embedded in the globin, and in the middle of it is the iron, and that's what attaches to oxygen and carries oxygen around your body. It was in the last lecture. You can. Yeah, no. A blood cell is packed with proteins and like millions of proteins. Those proteins are called hemoglobin. The hemoglobin is actually what carries the oxygen. There's this molecular framework inside and the heme is a small organic. You'll see it. It looks a little bit like a molecular dream catcher or something, and the iron's at the middle. It binds the oxygen. It's in the previous lectures. You can go back and check it out. All right, so this oxalic acid is really highly concentrated in spinach, and it's actually in a lot of leafy greens. It adds a little. Sometimes you'll eat some greens and they taste a little bitter. Often it's the oxalic acid in them that is causing that bitter flavor. The oxalic acid is a bit of a problem for some people. Some people's bodies can't metabolize oxalic acid very well, and or if you have a diet that's really high in them, you can get kidney stones that are made of pretty much pure oxalic acid. The oxalic acid drops out of solution. It is not very soluble, particularly when it's bound up with iron. It's not soluble, which is why your body can't absorb it very well. But if you do absorb a bunch of this stuff, because it's not soluble, it doesn't go into solution in your urine especially well and can accumulate. Just like if you, does anyone ever have like a water from a well that was really soft and you get the like lime buildup around a faucet, maybe a drain somewhere? It's similar to that. So you can get these kidney stones, and that's what you see here. That's a picture of a staghorn kidney stone. Looks pretty amazingly painful to have in your kidneys. Anyone ever had a kidney stone or known somebody with a kidney stone? They're nasty things. But that's from the oxalic acid binding to different metals, but usually iron. All right, so that's hemoglobin, so I've established that hemoglobin is an excellent bioavailable source of iron, and then vegetable sources like spinach are actually a pretty poor source of iron. We've been talking about the three different sources, animal sources of iron. There was the hemoglobin. The second was ferritin, and the third was myoglobin. So ferritin is a storage molecule for iron. And it turns out that there's a lot of ferritin in your liver. Your liver stores quite a bit of iron, and this is why liver itself is extremely high in iron, because your ferritin's there. So if you look at 100 grams of pan-fried chicken liver or simmered chicken liver, you have 13, 11, 12, something like that, milligrams of iron. And in a similar 100 grams of spinach, if you'll cast your mind back, there was only about 2.7 milligrams of iron in those samples. So chicken liver is indeed exceptionally high in iron, and it's exceptionally more absorbable. So in 10 subjects, what do I have here? Geometric mean absorption from 5 milligrams of ferritin iron was 3.8% when taken without and 3.2 when taken with food. Okay, so the point here actually is that ferritin, although it is a rich source of iron, that iron is no more bioavailable to the body than the vegetable sources actually. And that the really bioavailable iron that is in liver is the hemoglobin, not the ferritin. So even though there is a lot of iron in there, most of the iron that you're going to be able to absorb from the liver is in the hemoglobin, not the ferritin. So ferritin itself is not actually a very good source of absorbable iron. And I guess that would mean then that I don't have a statistic as to how many of the 3 milligrams of iron is ferritin versus hemoglobin. So the question then is it better to eat liver versus just standard meat to absorb your iron? I'm not sure. I think I have a table coming up that looks at that. Let's.
Where do you get ferritin?
So ferritin's in liver. It's in liver, and people say that liver is a really high concentration of iron. But the point that I was making here in this slide is that ferritin actually is not especially absorbable. Only 3 to 4% of the iron that's bound in ferritin is absorbed by the body. So if you had, 10 milligrams of pure ferritin, that means you're only going to absorb, 300 micrograms or whatever of iron that way. And that actually the iron that you're absorbing from liver comes from the hemoglobin that's in liver, but there's other sources of hemoglobin, right? I used to be friends with a boxer, and he would swear by eating liver. He would just, eat tons of fried liver and onions because he thought that he was absorbing a huge amount of iron. And he was certainly consuming a lot of iron, but maybe it was just making him constipated and not actually giving him a bunch of absorbable iron, more than a steak might. Yeah.
Eat it with onions?
My pal?
Yeah.
Fried onions. Blackened onions and liver. That's how we liked it.
Can you get, I feel like the point.
Oh, I see. No, but the vitamin C is what coordinates the free iron that you would have in like spinach or something like that. So lemon over your spinach will make the iron a little bit more absorbable. In ferritin, the iron is actually embedded in a protein that is not going to be coordinated by the ascorbic acid at all.
That's why.
Which is more accessible. Yeah. The iron in chicken liver is more accessible because there's hemoglobin, not because there's ferritin. Yeah. All right. Yeah. So here is the table that I was talking about. Looking at beef heart, brain, liver, spleen, kidney, and then whole blood. You can see that There is a fair amount of iron in liver, and this is milligrams per 100 grams of raw protein extracted from those tissues. But the stuff that was in liver, a lot of it is ferritin and not as absorbable, whereas blood, probably the most highly absorbable source of iron is going to be in that blood sausage that we talked about, as unsettling as that might be to some of you. And then comparing it to other cuts of meat, you can see that the other pork, ham, bacon, and even just like standard beef is relatively more modest in its content of iron, although that's going to be primarily hemoglobin-based iron rather than ferritin. All right, so you're not into black pudding, you're not into chicken liver or beef heart. What do you actually want to eat? Well, how about some Thanksgiving turkey? I'm sure many of us have just partaken of that. Well, as we're all very familiar with the Thanksgiving platter, there are dark meat people and there are white meat or light meat people. Nary the twain shall meet. What does that even mean? What does this mean? Well, it turns out that there are more than one type of muscle fiber, and this isn't just in turkey. This is in you, all of you. In fact, there's more than just two. There's several types, but there's two general categories. So there are these slow oxidative muscle fibers. This is what we see as dark meat. And there are fast glycolytic fibers, which we see as light meat. So most muscles in your body have a mixture of the two of them. Some muscles have more of one or more of the other. So for example, your extraocular eye muscles, the eye muscles that you use to move your eyes around or blink, those muscles are mostly fast glycolytic. I guess before I describe that, I should tell you what they do. So a slow oxidative muscle is essentially one that has been geared for aerobic activity, whereas a fast glycolytic one is one that's been geared for anaerobic. So an aerobically tuned muscle is one that you're going to use. So like any of the long distance runners in the classroom or the Nordic skiers, or if there's any swimmers out there, you guys tend to work on developing your slow oxidative muscles. These are muscles that enable you to have a steady output of performance, of force over a long period of time that always requires oxygen, that you're able to send oxygen to those muscles for the long term, right? And the way these muscles do this is they have a molecule called myoglobin in it. Myoglobin is that little thing that I have drawn in the corner there. It's like hemoglobin. It has heme in it, but instead of being a tetramer, it's a monomer. It doesn't have quaternary structure. It only has tertiary structure, and it has iron in it. Because it has iron in it, it's colored just like the hemoglobin in your blood is colored, and it is what turns dark meat dark. All right. So myoglobin is a storage molecule for oxygen in these slow oxidative muscle fibers. All right. So that when that muscle, if you're pushing that muscle towards what's called the anaerobic threshold, maybe some of the athletes in the class have heard of anaerobic threshold before. If you're pushing towards that anaerobic threshold and you just bounce past it for transiently, that myoglobin can release the oxygen that it's been sequestering in the cell and keep that cell in the aerobic zone. So it's a repository for oxygen when you're doing aerobic activity. Fast glycolytic muscle fibers, these tend to be ones that are in muscles that you're not going to use for endurance activities. So these may be muscles that like a bodybuilder may use, or like a football player or something like that. Some of the other muscles that aren't in the large muscle groups of the thighs. A football player is not a good example actually, because they use both. The ultimate fast glycolytic muscles are the extraocular eye muscles. You're never like, nobody is running a marathon with their eyeballs, right? You're not like constantly moving your eyes back and forth and carrying a huge weight with them. Instead, what you want is rapid response, right? You want a rapid response, but there's not a long-term sustained need for energy in these fast glycolytic fibers. Anyways, dark meat is the upshot of all this in terms of the biochemistry of food, is that dark meat is a much better source of iron for you than light meat is. I know a lot of people like white meat, like turkey breast or whatever, but the turkey leg is a better source of iron for you because it's got this myoglobin. Myoglobin has a similar bioavailability of iron as hemoglobin has. All right, you guys following this? Is some of this useful to you? I hope. Maybe making choices. Yeah.
I've heard that I've heard that dark meat is like higher in fats.
It may be a little bit higher in fat, but that is purely based upon the anatomy that the dark meat is being sourced from. It tends to be closer to fat because, without getting deep into more metabolics than you guys are probably prepared for, there's two types of metabolism that you can have. I talked about glycolysis a little bit. And the burning of glucose to make ATP in the citric acid cycle. That is glycogenic or glycemic metabolism, right? There is another sort of parallel branch called ketogenic metabolism. I touched on it, but I kind of like skipped over it at the end of the last unit. And ketogenesis is often happens when people are burning fat rather than sugars, and so maybe large muscle groups that have endurance potential. They are going to have myoglobin. They're going to be dark because they want to be aerobic. But because of their functional need to have a long-term or endurance performance, maybe they will run out of glycogen. You basically deplete the glycogen stores in your body after about 45 minutes of continued, anaerobic threshold activity. And so at that point, you begin to burn fat. And so the fat can be in those regions more because that muscle needs to mobilize that energy source. Yeah. Okay. Did that sort of answer that question without getting too deep? Anyone else? Questions about this? Does everybody follow what I gave you here? I feel like I'm not being super articulate today. All right, back to Popeye. Turns out that this myth about Popeye being obsessed with spinach because of its iron content is due to an error in a food science paper that was published in Germany in 1870. Or at least that's what you would believe if you read the media. So I don't know if there's any people who have deep skepticism of the mainstream media, but I imagine some of you at least are familiar with the Guardian and would think of it as a reasonably respected newspaper. Certainly it is. And this is an article that came out, what was this, last spring? A year and a half ago. So what does he say here? This guy, Yotam Ottolenghi. And Yotam Ottolenghi, I should say, is, I'm not really familiar with him, but he's like a Michael Bourdain kind of guy. One of these like foodie, guru people. He's got, a bunch of cookbooks and food shows or whatever. I don't know much about him. So what does he say here in this Guardian article? Other mistakes have had rather more far-reaching effects, notably spinach, which owes its reputation to an iron-packed superfood to an even bigger howler. German scientist Erich von Wulff misplaced a decimal point when he was writing up his findings, and he said that spinach leaves had 3.35 milligrams rather than 3.5. And so he goes on to claim that this is why Popeye, et cetera, et cetera. Okay, so he says this. The Wall Street Journal also begins starts beating the same drum. 1870, Erich von Wulff, et cetera, basically saying the exact same thing as the Guardian article. So this was a little bit earlier. This was in 2012. It took a few years for the Guardian to catch up. Even the Daily Mail. Sorry, Popeye. So the Daily Mail is a less prestigious, but whatever, no less widely read, probably newspaper out of England. Sorry, Popeye, spinach doesn't make your muscles big. Experts reveal, blah, 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 blah. Turns out all of these news articles are derive their claims from this book written by this guy, Samuel Arbsman. All right, so let's go to the source here. Hi, here he is, Samuel Arbsman. He is an applied mathematician and a network scientist at Harvard. And that seems like that would be a pretty sexy job to have. And he's at what's called the Kauffman Foundation there, which is some sort of social science institute. He writes for all sorts of big publications, The Times, The Atlantic, Wired, etc., on and on. And he published this book called The HalfLife of Facts in 2012. This was certainly the book that the Wall Street Journal was citing in all these other articles. What does he say here? Let's read it straight from the horse's mouth. Popeye, with his odd accent and improbable forearms, used spinach to great effect, sort of anti-kryptonite. It gave him strength and perhaps his distinctive speaking style. But why did Popeye eat so much spinach? What was the reason for this obsession with such a strange food? The truth begins more than 50 years earlier. So he begins to tell the story about how Erich von Wulff misplaced a decimal point. Once this incorrect number was printed, second paragraph, spinach's nutritional value became legendary. So when Popeye was created, studio executives recommended he eat spinach for his strength due to its vaunted health properties. Apparently, he goes on to talk about how much spinach people began to eat. The error was eventually corrected in 1937 when someone rechecked the numbers, but the damage had been done. It spread and spread, and only recently has gone by the wayside, no doubt helped by Popeye's relative obscurity today. Has anybody, I didn't even occur to me, had anybody never heard of Popeye before I started talking about this cartoon character? Okay, good. But the error was so widespread that the British Medical Journal published an article discussing the spinaches in 1981, trying to finally debunk the issue. So I'll say this. This guy, Arbsman, the whole book, The HalfLife of Facts, is basically, he's a scientist that looks at the exponential spread of information, and he's a network scientist, and he looks at how viral ideas spread or whatever. And this book is about how false scientific claims get seized upon and how they spread throughout culture, right? So he essentially is a scientist that studies how incorrect ideas are spread through science, all right? Seems like a worthy field to pursue. It turns out that life is ironic. And the actual data that was originally published was in this German journal. And this guy, Samuel Arbesman, didn't even go to the original German article to look at the data for himself. I haven't gone and read his book to find who he was referencing. But if you look at the actual data, that claim that it was a decimal error was actually erroneous. And so here I'm highlighting the actual data. You see ferric oxide in spinach, and it's all those weird words on the left. That's all in German. So evolutionary ecologist from Germany who looked at the original German article, Dr. Joachim Dag, pointed this out on a blog he had, Natural Histories, Historical Notes on Ecology and Evolution, a pretty interesting blog. The guy's clearly a thorough individual. There's a long discussion of this error, but it's kind of funny to me that there's a third layer of this myth about why spinach was embraced by Popeye. So Dag says the decimal error is a myth. It never occurred. False reputation of spinach was due to unreliable methods or poor experimentation. That is, errors were inherent in the experiments, not in the data treatment. In fact, it was reported that it was about 3.5 milligrams by the original paper, and the real value was closer to like 2.7, like that. So a pretty modest error in terms of reporting. And I don't know what this guy Samuel Arbesman, whether he's aware of being called out, because this other guy Dag from Germany is pretty obscure. But I don't know. It's interesting. This doesn't resolve the problem. There may be a fourth layer to this myth, which I found kind of interesting as I was doing my research on this. So why was there this notion that spinach was high in iron? And the reason that Popeye might have fixated on it could be related to the fact that during World War II, French sailors in World War I, not World War II, in World War I, French sailors and soldiers that had been hemorrhaging, they'd been injured, they were given wine that had been fortified with spinach juice because they believed that the spinach juice had lots of iron in it. An injured soldier doesn't want to take a shot of spinach juice, but you put some wine in it, it's easier to get it down the hatch. So that may be the timing. The timing of all that is well enough to be something to be considered. All right. Otherwise, if it wasn't the iron, then what? There is an answer to this question. Why does Popeye like spinach? But I'm not going to tell it to you. We're gonna slowly discover it together. All right. So if it wasn't the iron, then what? What about vitamin C? So we had talked about how vitamin C helps you absorb iron. There certainly is vitamin C in some spinach. Let's observe vitamin C. So the whole notion of vitamin C happened at around the same time as the advent of Popeye. So here on the left is a can of orange juice, the way it was originally marketed. In 1920, orange juice was a pretty fringe product. It came in cans, it was boiled, it was quite flavorless and bitter, apparently. So not something. Huh? Maybe they are tomatoes. Yeah, okay. Yeah, all right. Well, I got a bad image up there. But OJ was canned, it was boiled, and it was bitter. So pardon my my rapid Google imaging mistake there. But it's hard for me to actually, I guess, find an image of canned orange juice from that era. Yeah.
Why did they boil?
I don't know, actually. Probably to pasteurize it, to sterilize it. Because orange juice is a pretty good medium for growth. And if you boil it, it won't ferment and go off. So you boil it and can it, and it's like stabilized. They didn't have the like transportation infrastructure. That was like the freeway system, and like shipping food all over the place was still nascent in the country. So somebody who lives in Maine wants to drink some orange juice. You put a can of it together and ship it in a truck. Take the slow boat. We live in a different world now. But anyways, there was this radical shift in the public perception of orange juice just in the span of 10 years to this notion of orange juice as a health drink.
Sounds
Orange juice as a health drink?
No, they can't.
Yeah, it does. I'll have to look harder for an image of it. All right, and this whole transformation of orange juice, and indeed, as we'll find out, the broader society's perspective on vitamins and minerals is due to this guy, Elmer Werner McCollum. So he was a biochemist at the University of Wisconsin, kind of an interesting character. There's ample examples in the history of science or even just in the history of famous people, of people that have made significant contributions and that have brought them to fame, but it's also brought some of their weirder aspects to light in public, and he's one of these guys as well. So we'll focus on the upsides of him at first. He had this. His whole thing was eat what you want after you have eaten what you should. That was his nutritional advice. Eat what you want after you've eaten what you should. This guy discovered vitamins A, B, and D. And vitamin A was in 1912 or 13, something like that. Some of I forget which of the B vitamins he discovered, but that was soon after that. It was during World War II, or World War I, 1918. And then D was in the 20s. So because of all this, he published this textbook in 1918 at the end of World War I called The Newer Knowledge of Nutrition. And it became the Bible, the nutritional Bible for the nutritional community at the time. The use of food for the preservation of vitality and health. And he talked in this book about the ability of vitamins to extend life and heal wounds and cure cancer. He warned about vitamin-deficient diets as being the scourge of existence. And this, he also had, so this became an amazingly marketable perspective that was seized upon by a lot of different companies in the food industry. One of the things that sprung up was the vitamin industry. So one a day goes back to this time of Elmer McCollum. And so this was you'll find all the vitamins that you need in a convenient pill. Take one of these, and you'll never have a vitamin deficient diet again. He had this idea called acidosis. So this is where we begin to verge into the territory of quackery. Acidosis, the word that it has a couple meanings. The current word that any medical professional would talk about is a real thing. Acidosis happens when your blood becomes too acidic because you're hypercapnic, you're not blowing off enough carbon dioxide, maybe you've been exercising too much, whatever. Acidosis is a real thing. But he wasn't, and this comes after exercise. The acidosis this guy was talking about was, he said there was an excess of acid in the bloodstream, which can happen, but he believed that it was supposedly caused by consuming the wrong kinds of foods. so that if you ate eggs, meat, bread, he said they were acid producers. And he said that it caused fatigue and lassitude in his book there. His prescription was to eat lots of citrus fruits and lettuce because counterintuitively, a citrus fruit is going to make your blood less acidic. It's going to produce alkaline compounds in your blood. All right, so this is not actually borne out by any empirical evidence. But we'll get to that in a bit. So the citrus growers rapidly jumped on the acidosis bandwagon, and so this is a tract that was put out by Sunkist company in Florida. It says Sunkist recipes for everyday and vigorous health, and in it they have this payroll scientist who wasn't actually a scientist, but Dr. Sansom says practically all diseases and all types of poisoning are associated with varying degrees of acidosis, as if he knows what he's talking about. The cause of acidosis lies mainly in the foods we eat. It's almost a universal malady because we eat too much bread, fish, meat, eggs, cereals, but they're acid-forming foods. And what you really want, so to say, which is in the process of oxidation, burning in the body, leaves an acid ash in the blood. So eating meat and eggs is going to leave acid ash in your blood. And the way you can get around that is to drink some Sunkist orange juice every day, essentially. And then they're clearly targeting young women here. So this is the page directly following, opposite of that page I took the quote from. And the caption on this image here, we have this young woman clearly attracting the charm with her charms, these two dashing young men, and this other woman obviously overwhelmed by fatigue and lassitude in the back, saying, Estelle seemed to lack vitality, didn't even make an effort to be entertaining, hence she did not attract the men. Acidosis is the word on almost every modern physician's tongue. So here's some marketing driving these misperceptions, misinformation about it. This still exists. If you go in any health food store and browse the fringe library that a health food store has, you're going to find some kind of book. There's all kinds of guys out there that are repackaging the same notion of Elmer McCollum's from 1918 into some new shiny book. This is a chart that it was one of the top hits on the Google image search when I was throwing this together. The food impact on the body, pH chart. So acidic, acid-creating substances are acidic substances, meats, bacon, sausage, processed cheese, sweets, all these evil foods. Certainly none of those are particularly good. But on the other side, these supposedly alkaline-forming foods, which are so health-conferring, we have fresh lemons. Fresh lemons are certainly not alkaline. They are extremely acidic foods. Kimchi, other fermented vegetables, raw spinach. All food that's really good for you, but it's not going to alkalize your body. All right. So that's basically that. Debunked that myth. Next time I'm gonna talk a little bit more bunk about this guy, and then we'll finish up vitamin C. But that'll be Monday. So Friday we have Jeff Wolowitz from Heiwa Tofu coming to talk to the class in here. All right? Everybody good? Anyone need any help from me? Everyone happy? Yes, you sent me an email about Thursday today, right? And did I respond to that?
No.
I did in my mind.
Okay.
Okay.
Sorry.
Yeah, it's fine. Yeah.